Okay, so 6.4, we're going to talk about conditional probability. What does that mean? Sometimes the knowledge that one event has occurred changes the probability that the other event has occurred or will occur. Think about the probability of being in a car accident increases if you know it's raining outside. Suppose that the pass rate on the AP exam is 80%. That is, for a randomly selected student, the probability that you pass is 80%. However, if you know the student got a B in the class, then the probability increases to 95%. That is, for a randomly selected student, the probability that you pass, given you have a B, is 0.95. So the notation is the probability that you pass slash B is 0.95. So that slash is the part where you know it's conditional, and it's a given. So probabilities in the form of probability of A slash B, those are called conditional probabilities. So it's the probability event of A occurring given that event B has already occurred. When finding these probabilities, you only have to consider events in the sample space of the event that is known to have taken place. So our big example of the day is we're going to talk about the Titanic. So the following data is about the 2,201 passengers on the Titanic. 367 of 1,731 males survived, and overall 711 people survived. Explain this in a two-way table with gender and survival as the variables. So a two-way table, you'll see a lot of those. We've seen them before. Is a way to summarize the relationship between two categorical variables. It lists the outcomes of one variable down the left side, the outcomes of the other across the top, and the frequencies or the relative frequencies within each cell. So we're going to do gender. So we're going to have male, female, and I'm going to put a total column. They don't always have a total column, but for today it's going to be nicer. And then we're going to have they either survived the Titanic, they died, and then total. So by just giving you 3 pieces of information, we can find the rest of the stuff. So 2,201 total passengers, so that's my total. 711 people overall survived, so that's my survived total. 367 of the 1,731 males survived. So 1,731 males, 367 of them survived. Now all I'm going to do is take my calculator and subtract to find the other parts of my two-way table. So like female survived, I'm going to do 711 minus 367. 344 to get my total of that died, 1,490. To get my male that died, I'm going to subtract 1,364, and then I'll subtract these two, 126, and then I can either subtract these two or add the female. Let's add them, just because. So it's 470. Okay, so now let's do a bunch of probabilities. So suppose we randomly select a name from the Titanic passenger list. Usually what I explain to them is there's a Titanic exhibit. It came to Greenville Village like a couple years ago. And usually what you do is you get a little card, and it's got like your name on, a name of a passenger, and then like a little info, and you go through the whole exhibit, and then at the end it tells you whether you see a big wall, and it tells you whether you lived or died. So it's kind of like we're trying to do that. So what's the probability that you get a card of a survivor? Well, how many people survived? There were 711 people out of 2,201. I'm going to convert these to percentages only because I feel like it's easier to see kind of better than the fractions would. You don't necessarily have to. Remember, we do want to reduce our fractions. You can hit math, frac. This doesn't reduce. And you should get, so 32 0.323. So 32% of the people on the Titanic actually survived. What's the probability that you get a male passenger? Well, male, 1731 out of 2,201. Oops. I keep hitting the wrong thing in the calculator. So about 0.786. So 78% of the people on the Titanic were males. And a lot of that little history lesson was because females were not allowed to travel alone. Also, many of the workers on the Titanic were male. So what's the probability you get a female and they survived? So female and they survived would be 344 out of 2,201. And that's about 15.156. So about 15% female survived. Now, the rest of these are all conditional probabilities. So, again, the second part is becomes your denominator. So, what's the probability that they survived given that they were females? So, out of all my female passengers, how many survived? So, now this changes. It's 344 over 470 because I'm only looking at the females. So, now if I do that, divide that, that tells me about 73% of all the female passengers actually survived. So these are much different probabilities if you look at it that way. And that's because, right, women and children first. Now, what's the probability, given that they survived, that they were male? So we're looking at all the survivors, the probability that they were male. So 367 over 711, about 0.516. What's the probability that, given that they were female, that they passed away? So again, out of all the females, I had 126 pass away. It's 0.268. These two are actually complements of each other because you're looking at the same column, right? One's the survived, one's the died. What's the probability given that they died, that they were female? So 1,490, 1,364. No, I looked at male. 126. About 8% of everybody that died was female. Again, because there were more male passengers anyway. And what's the probability out of all the survivors that they were female? So out of my 711 survivors, female was 344, so about 48%. So it just shows you the difference between looking at something in terms of the total versus looking at something very condensed down. So there is a formula for this. The formula is on the back. So let E and F be two events. The conditional probability of event E, given that event F has already occurred, so E/F, is equal to E and F over F. Now, this is on your formula sheet. So like I said before, there's only two real formulas for this chapter. This one from section 6.2 and then this one from today. That's it. So each got to go from there. Again, we sort of did this without knowing it. What's the probability that, given that they survived, that they were female? So again, that they female and they survived over the probability that they survived. Oops. So we knew that there were 711 people that survived. 344 were females and survived. So we did that. I just didn't write it out like that. But that's what I was doing in my head. Another example, this also works. You're going to see this a lot more with conditional probability in terms of a tree diagram. So given that 1,000 football players, 40% of them are reported to take steroids. Our test is 90% accurate. If Bobby Bubba Jones tests positive, what's the probability he has taken steroids? So you're going to see conditional on a lot of with this kind of stuff. So you're going to do a little tree diagram. So their football players are either taking steroids or they're not taking steroids. So we have 40, 60. Now your test is 90% accurate. So if I'm testing for steroids, I should test positive 90% of the time. I still am going to have that 10% false negative. If I'm not taking steroids, I should test positive 10% of the time and negative 90% of the time. So we're looking at the probability given that Bobby Bubba Jones tests positive that he's actually taking steroids. So given that he tests positive that he's actually taking steroids. So the positive part comes second. So if I write out using the formula, we're going to find the probability that he's taking steroids and he tests positive over the probability he tests positive in general. So steroids and test positive would be 0.4 times 0.9. So you kind of like go through the tree diagram, that's like your and. So 0.4, 0.9. I don't know why that's there. Now, the probability he tests positive, there's two ways for that to happen. He can be taking steroids and test positive, not taking steroids and have a false positive. So we're going to multiply and add. So 0.4, 0.9 plus 0.6, 0.1. So this is 0.36 over 0.42. So you get 0.8857. So 85% chance that if he tests positive that he's actually taking steroids. Now, the 90% accuracy, some students will always ask me about that. Shouldn't that be 90% because the test is 90% accurate? The test is only 90% accurate when it's a 50-50 chance of him actually taking steroids. So if we change that to 40%, then that's why this kind of goes down, if that makes sense. So just knowing that we're going to do a lot of these in the next couple of days, so you'll see a lot of these and a lot of two-way tables.